Hello, and welcome to the first video of Real Analysis. Today's objective will be to introduce the idea of an upper and lower bound of a set or interval. We will start with a formal definition for an upper bound. A real number u is called an upper bound for a set A, provided that for all A in the set A, it is true that A is less than or equal to u, and if a set A has an upper bound, then we say that A is bounded above. So, this begs the question, what does an upper bound mean visually? Likewise, what does a set being bounded above mean visually? Let's say, for example, you were looking at a number line at the closed interval from -2 to 4. Then, we can see that for the value 4 or any greater number, they will be greater than or equal to every value in the closed interval from -2 to 4. This indicates that 4 is an upper bound, 5 is also an upper bound, and any greater value will also be an upper bound. Since we have the existence of an upper bound, then our interval is bounded above. Looking at another example with a number line to go along with it, we see that for the closed interval from 3 to 7, both 7 and 8 are examples of upper bounds, since they're greater than every value in the interval. Further, the open interval from 0 to infinity will have no upper bound, or is unbounded above, meaning there is no number u we can choose such that every number in the interval from 0 to infinity will be less than. A useful proposition is as follows. If u is an upper bound of A, and x is such that x is strictly greater than u, then u is not in A. To show this, we'll use a quick contradiction proof by first assuming that x is greater than u, and then assume that x is in A. This would imply that x is less than or equal to u, since u was an upper bound for A, but this contradicts the first assumption that x was greater than u. Thus, x is not in A. Moving on to another proposition, we will now formalize a proof that the closed interval from -3 to 2 is bounded above. We can do so with a direct proof by assuming that we have some arbitrary number x within the interval. Then unpack the definition of a closed interval to get the inequality that x is between -3 and 2. Since we only care about showing the interval is bounded above, we look at the right side of the inequality, which states that x is less than or equal to 2, which, if we remember, is the exact condition for 2 to be an upper bound for the closed interval from -3 to 2. Since there exists an upper bound, the interval is bounded above. We can see this visually, that the interval is clearly bounded above by the values 2 and anything greater than 2. Next, we'll look at a more complicated set, the set of real numbers such that the absolute value of 3x minus 2 is less than 4. Before we start, we'll do a bit of scratch work using the absolute value and inequality. After a little algebra, we see that the absolute value of 3x minus 2, which is less than 4, corresponds to the open interval from -2/3 to 2, which, by looking at a number line, clearly shows that 2 and anything greater than 2 will be an upper bound, since those values are greater than the interval. Now we can start the proof. We begin by picking an arbitrary value within the set, then unpack the definition of the set, do our scratch work, and pick out the part of the inequality that we want, which is x is less than 2. We further know that since x is less than 2, then x is less than or equal to 2. Since all values less than 2 are also greater than or equal to 2. 2 now fits our definition for an upper bound. Thus, the set A is bounded above. Moving on to our second definition, a lower bound of a set is the exact same as an upper bound, but instead of being greater than or equal to all elements, a lower bound will be less than or equal to all the elements in the set. Just like we did with upper bounds, we can visually represent lower bounds as well. Consider the closed interval from -2 to 4. We see that -2 and the values less than -2 will always be less than or equal to every number in the interval from -2 to 4, thus making these lower bounds for the interval. For an example, we'll look at the set of real numbers such that the absolute value of x squared minus 1 is less than 2, and show that it is bounded below. Once more, we'll do a bit of scratch work to get our lower bound first. Using inequalities and algebra, we get the inequality that x squared is between -1 and 3. We can use the fact that x squared is less than 3 to say that x is between negative square root 3 and positive square root 3. In particular, negative square root 3 will be our lower bound. Now, formalizing this into a proof, we start again by choosing an arbitrary number in our set. We unpack the definition of what it means to be in the set A, then use our scratch work to determine that negative square root 3 is a lower bound of A, telling us that A is bounded below as desired. Now we'll look at a common set of numbers in analysis called the harmonic numbers, which I'll represent in 3 different ways. Our goal being to prove that the harmonic numbers are bounded, meaning bounded below and above. Visually, the harmonic numbers start on 1 and move towards 0, telling us it's most likely bounded between 0 and 1. The proof will be split into 2 parts. We will start by proving the harmonic numbers are bounded above. We can do so by choosing an arbitrary element A, which we can define as 1 over n. Further, we know that the natural numbers are greater than or equal to 1, so 1 over n will be less than or equal to 1 over 1, since the denominator can only be smaller and 1 over 1 is the same as 1. Thus, 1 over n is less than or equal to 1, giving us an upper bound for the harmonic numbers. Now we will show that the harmonic numbers are bounded below by 0. We pick another arbitrary element within A, call it b. Once more, we define b as 1 over k, and notice that since natural numbers are greater than or equal to 1, they are also greater than 0. Thus, we can conclude that 1 over k will be greater than 0, and so it is also greater than or equal to 0. Thus, 0 would be a lower bound for the harmonic numbers. Since we have that A is both bounded above and below, we conclude that the harmonic numbers are bounded. Another type of problem we can encounter is the one as follows, where we have some set A that is bounded above, and we want to show that another set B, which is defined as the set of reals such that 2 times the reals is in A, is also bounded above. To give a general idea of a proof sketch, we'll take an arbitrary element in the set B and use the definition of B, which relates back to A, to get the relation that 2b is less than or equal to u, where u is some upper bound of A. Then, solving for b, we see that b is less than or equal to u over 2, thus making u over 2 an upper bound for b, meaning the set B is bounded above. This next proposition will formalize a proof for. We're showing that if we have some set A, which is bounded above, then the set B, defined as such, is also bounded above. Another way of saying that is, if A has an upper bound u, then B has an upper bound 3u minus 2. Or, if little b is in the set B, then B is less than or equal to 3u minus 2. Jumping into this proof, we start by establishing an upper bound u in A. Then, take some arbitrary b in B, unpack the definition of being an element in the set B, which gives us the b equals 3a minus 2. We then can manipulate the fact that all elements in A are less than or equal to u to get that 3a minus 2 is less than or equal to 3u minus 2. Since we know that b is equal to 3a minus 2, we have that b is less than or equal to 3u minus 2. Thus, 3u minus 2 is an upper bound for b. Looking at one more example, we have that if A is bounded below, then the set B is bounded above. We follow the same steps as before, use the definition of a lower bound for A, then pick an arbitrary element in B and unpack its definition. In this case, we know that since 7 minus 4b is in A, we can say that 7 minus 4b will be greater than or equal to L, the lower bound of A. Solving for b gives us the inequality that b is less than or equal to 7 minus L over 4, making this an upper bound for b. Some interesting related statements that may prove useful in the future are: if A is a subset of B and B is bounded above, then A is also bounded above. If A or B is bounded above, then A intersect B is also bounded above. If A and B are bounded above, then A union B is also bounded above. And lastly, the empty set is bounded above and below. Our final proposition today will be that the interval including 0 to infinity is unbounded above. A standard technique for showing something is not something or unbounded is to use contradiction. So, we begin by assuming for contradiction that A is bounded above, which means there is some upper bound u. Since 0 is in the interval, we can say that u is greater than or equal to 0. Thus, u plus 1 will also be in the interval, since u plus 1 is greater than u, which is greater than or equal to 0. But, since u is an upper bound, u has to be greater than or equal to u plus 1, since it's in the interval as well. As we know, this is not true, this is a contradiction, therefore, A is unbounded above. That's all for today. Thank you for watching.